So we're back with another enthralling installment.
Alright, time for the Draftscience.com video presentation. I'm tired. Anyway, so I did a few more lever experiments. I was playing a little bit more with the coupled oscillator, and
Which is not a lever, but anyway.
not a huge amount of progress, except it's it's not bad as an experiment, but I have to increase the frame rate. So either I have to use better lighting, or I have to use a better camera, or I have to increase the distance they move, or something. I have to reduce the velocity, reduce the weights, which I really don't want to do. So I have to.
Right, so the other day it was all about you needed more velocity, more speed to make it more efficient, but now you've got to reduce the speeds. That's quite interesting, isn't it?
Consider what the best approach is, but this is close. I mean, it looks close. Let me just put it that way. But again, when you're doing frame rate, you're doing 2.5.
It looks close. What you'd probably be better doing is actually making some, proper measurements. Seems like not a good plan.
Half versus 3 for a certain distance, and the velocity decreases rather rapidly because of the gravity thing. So it's not an ideal circumstance.
Gravity thing, yeah, that's kind of ever present. That's something you're really gonna have to deal with.
I thought I would have a better capacity to get very good frames, and they're really, frankly, blurry and not so good. They're not going to be good enough, so I have to get it better somehow. So I was thinking maybe using one of Brozo's techniques of sound, and trying to measure the time difference.
Right, so you want to use one of Stephen's methods that you basically rubbished, okay?
Between when they hit some kind of fixed distance, but then the fixed distance gets complicated because the lever isn't always perfectly straight, so lots of things to consider. So I'll play this, and then there's a link to this raw video if you want to look at it and analyze it. Yeah, so, not there quite yet, but it's close. I mean,
close.
It's close. So you can see distance-wise, you'll see that the two pretty, they reach similar heights. Similar. Not quite, but similar. I'm trying to get my finger on there, but I'm trying to get the lever straight. Not quite. So you can see we start about there, and, this one's not going to land perfectly straight. But, it's pretty good. But obviously
pretty
you can see it's got a lot of losses in it because it doesn't continue very long.
Judging by eye.
Obviously it's not
no
perfect.
measurements, just
so this was a long way, so this one should
like
almost go off the screen.
Okay.
So let's see if it does that. Well, see that one's about, it was a half-inch hanging over, and this one had like an inch hanging over, so it's not a complete conversion, but it's closer than the other experiments. And the other problem is this is not a very thick steel, and I can see it does bend a little, so it's really not going to handle the 2 mass very well, but we'll see. So I'm above the line again, and this one's not falling very straight. Yeah, so that's a real failure. But you can see how subtle it is. I mean, you really do have to wait until everything works just right, and then you get a good result, and then you have to wait for another good result.
Yeah.
So half inch or so.
You find that, when you're performing experiments, there's a lot of trial and error in it, and you have to keep doing it over and over, and it's quite painstaking. It's not just as straightforward and as simple as you believe it to be.
Way short. Okay, so that wasn't as good as I thought it would have been. So, yeah, I guess it looks better when I was doing it than it looks better than it does in the video, but it's closer. That's all I'm going to argue. So this one was really crooked. Yeah, very crooked. So I think this second one is probably one of the best ones. Let me see.
I mean, the thing is, when you've got controls, that takes the time out of doing run after run and getting fails. But what you're doing here is, there's no controls, there's no measurements, you've got no means of knowing anything really. What speeds, the distances on the lever, you're not really putting in the right place. The lengths of the pendulum could be off. There's a whole host of problems here because you've got no controls, you've got no measurements. When you put those controls and measurements in place, you get pretty consistent outcomes. Very consistent outcomes, actually. Despite you saying amateurs, can't do experiments, people can. Because the laws of physics don't actually change for an amateur to a professional. The laws of physics stay the same. So if you've been careful enough and put controls in place, you can get some very consistent and accurate results.
I fiddle with the fulcrum a little bit, and so considering that this one does start from a longer distance away, you can see it is starting from a further this way. So
yeah, because
it
it's
shouldn't
not
go as far
level.
because it's going a longer distance. So I guess if you recognize that flaw, it's a lot closer than, so that one's like this line here. So I guess I'll leave the mouse there. So it started about there. And yeah, so, we're talking, still an inch or
nowhere
so
near.
behind.
Yeah,
So whatever that would add up to, 80%, something like that.
whatever
So
it would
really
add
not
up
quite good
to.
enough. But I'll continue to work
Well,
on it.
that's
I'm
the
really
thing.
interested in catapults.
You're not whatever it would add up to, because that's just guessing again, isn't it? It's you're not measuring anything. It's very haphazard, very random, and you're just judging it by eye. You're just doing the very thing that you warn against, which is looks like, seems like.
Right now, and I'm just looking. So if anybody can find a serious catapult video, one where they just analyze the law of the lever or something and explain, as you go further out on the lengthen the catapult, it's basically a lever, and the law of the lever happens. You get twice the velocity with a lighter object. But there's not. I can't find any good. They're all kids videos. They're all just throwing pumpkins or some other kind of crap. No real good physics. What's the physics of the catapult? It all has to do with the angle you release at. When we're really after is when you release horizontally. What's the velocity implications? I mean, that's what I'm after.
Yeah, you might
Of course, I
struggle
can
with that.
believe it's the law of the lever. Twice the distance, twice the speed. If it's the mass is half, it's the same weight. So yeah, works fine. So that's
Right. Twice the distance, half the mass, same weight. That's what you just said. So you do understand that when you put the mass, the half mass, twice as far out on the lever, it's the same weight. So whether you're doing 1-to-1 or 2-to-1, you're trying to push the same weight.
what I'm tending to think I need to prove. Although Bro's already sort of proved it, I think it needs to be done again just to prove the point. I also did mess with some clay experiments, so I did it a little different.
Right,
it was way too sloppy. I mean, I didn't bother videoing it because it takes 6 tries before I get one.
You moaned about clay all this time, and clay is a terrible method of measuring energy. And now you're trying clay experiments, okay?
Good result. So I obviously have to find a better way to do it, but the idea was kind of simple. So I guess I'll throw that into this lever video, even though it's not the lever subject. I'm thinking of building the spring, so we'll do that first, the spring-driven lever. I really don't have to worry about doing the whole lever. So I'm thinking just even rubber bands or something to create.
So what Stephen Bruff has already done,
stretches rubber bands, you get a consistent force, and then do the 2 mass versus the 1 mass at twice the distance, and see what kind of velocities you can acquire, okay, by propelling them with the same force on this side. So the same force on this side.
I can pretty much tell you what that's going to do, but I think it might be more interesting for you to find out for yourself.
If it does their predicted 1.4 thing, when obviously I think it's going to do the 2 velocity thing, and nothing's going to stop it from being twice the velocity.
Right. So you say. So I think it's quite good that you're actually having a go at these experiments now, because while you've argued with Stephen Bruff and Disbar's Lab and Ian Gosling and Mindless Marbles and myself, and called all our results fake fraud results, you're not actually arguing with any of us now. What you're doing is you are dabbling with nature itself, and you are actually trying to defy the laws of physics in what you're trying to do, because what you're trying to do doesn't happen, which people have shown you, people have explained to you. You refuse to accept it, that's fine. I mean, nobody has to accept anything, but now you are actually playing with nature. And regardless of arguing with all of us and calling all of us fakers, you're now having to deal with nature itself. So you're not arguing with any of us now. You're actually arguing with the laws of physics.
And so it takes these problems out of the picture. Now, the problem is if I use the pendulum thing, then we still have the problem of getting the actual velocity as quickly as possible. So I guess I would have to set up a fixed distance for them to travel, so the distance has to be precise, and have some sort of belt that they hit or something, and then I can use sound.
You keep saying you're going to have to do this precise or whatever, but you don't tend to do that. You tend to do it extremely lazily and sloppily with no measurements, no precision of any kind, which in that case, you're not going to get good results. You are going to have to repeat it over and over and over to, to get something that looks like, seems like. But again, if you've taken no measurements, how do you know what you've actually got? You're just guessing.
To tell how fast they're going. Something like that. I mean, so I have to engineer something. Again, this should be done with people that have high-speed cameras and all this technology. They should be doing these experiments. And
these things have been done with high-speed cameras, and you refuse to accept it. So
sad tragedy that even my adversaries can't chime in or jump on that bandwagon. The bandwagon requesting better science videos, more elemental science, experimental videos done well and precise.
Well, people have done them well. I mean, Physics Michael has done some really good quality experiments. So is Stephen Ruff, so is Dispar, so is Miles Marbles, so is myself. All controlled, all videoed, all documented. Good, consistent results. Like I say, the laws of nature do not change for the amateurist. It's that simple. If you're a professional experimentalist, the laws of physics are the same for them as it is for us.
The fact that you people won't even agree that they shouldn't be wasting high-speed cameras on, blowing up balloons. They should be doing something better with the technology. And the fact that you can't chime in and say, yes, we really need to get the lab physicists, the experimentalists, to do these elemental experiments because they really haven't been done. I mean, we still don't have a decisive answer. Something as simple as a Newton's cradle. I mean, their theory says I swing this
I'm
half
pretty
mass.
sure, though, these experiments have been done time and time again. This is the thing, they're probably so mundane and boring and basic that, they don't feel the need to actually show them.
Into this 3 mass, okay, and I get 150 momentum, so to speak. I get 150% of the energy I started with.
Right, again, you get you get 150% of the energy that you started with. I don't know where you're getting those numbers from. A link, some link to that.
That's their theory. That we should be able to know whether that happens or not. Obviously, I say it doesn't happen, of course. No chance. Now, there is some slow motion. It's pretty well. It's some decent frame rate video of this experiment, and I think I probably should be able to analyze it. I just haven't gotten around to it.
Well, yeah, if you could provide a link to that, that'd be interesting. We'll have a look at that.
150% of this momentum. It's not going whatever 3/5 of the velocity or whatever the number would be. Anyway, so what was I going to talk about? Oh yeah, the other thing was the coupled oscillator. There's so many different experiments you could do. And,
yeah, there is.
None of them have been done. None of them. So you have the simple idea of the 2 mass here, and so I have it hanging from, I'm just if somebody wants to do the math, 88 inches. Okay, so I have 2 masses hanging from 88 inches. Okay, 1 mass and a 2 mass. And what I'd like to figure out, I'd like to figure out the distance of this arc. What's the math for figuring out how? I'd like to do the distance rather than the height. The height is harder to measure than the distance. So ideally, I'd like to just do what's the formula for detecting how far you have to go to hit that arc, where your distance is 4 times this distance. This gets kind of complicated.
Yeah,
anyway,
I mean, that's the thing.
I don't like it being too complicated.
If you want to drop something in gravity, obviously you know that you have to go 4 times higher, and you can just drop something from that distance, where you're now saying, oh, how do we do it on an arc? And yeah, just complicate the whole thing when you could just take a mass and drop it that distance in gravity, and that's it, done. You don't have to convolute it with all pendulums and arcs and make it more complicated.
Anyway, let's get back to this thing. So I had before had this hooked up to a lever. So this is fixed now. Fixed position here, some 21 inches between them. And all I had to do was put some rubber bands, okay, and put a weight here in the center. And
A weight in the center, okay.
Couple. So fairly well. I mean, obviously it has to be initialized right, or
so
both
you've
of them
added
just swing.
So you've now coupled them without the lever, but you've added a weight in the middle.
So once it's initialized, where this one's not moving and this one is,
I love that.
It stays that way for quite a while until it really starts to lose energy.
Once it's initialized, again, you're not getting that when you initialize it, you're not putting momentum in, you're putting potential energy in. And that will obviously result in that mass moving at a velocity, which will give you an angular momentum, and that will pass over to the other one. And obviously it'll never go twice as fast because you've only put enough energy in to make that two mass move. So when it converts the energy over, it's not going to give the same momentum, because for that one mass to move at twice the velocity would need more energy input to do that. So roughly, if you could measure it, it's going to be the 1.4 thing again, the square root of 2.
And so basically it'll go 2 swings, and gain its full velocity, and you can see it's going much faster.
Yeah, it's going faster. It's going about probably 1.4 times faster.
And then this one starts to move, and 2 swings later, it's at its full arc, and then it switches back to this one. So it's like every 3 swings, it switches from the energy being here to the energy being here.
Yeah, the energy, yeah.
So that is interesting, because I don't see too many examples of it demonstrated with uneven masses. And that seems kind of unfortunate, because, again, this is another demonstration where you can say there's no other place for the energy to be except in this object or in this object. You initialize the system with one amount of force, and the force has to either be here or here.
Yeah,
in a sense.
The energy is either there or there.
It's either going to have a peak velocity on this side, or it's going to have no velocity over here, or vice versa. There's no other choices besides this one having a partial velocity and this one a partial velocity. So there's going to be a point where this one has 0 and this one has all of the velocity, and then it'll switch to the other side, this one having all of the force. And you can see in their action what all of the force means. For the lighter object, it's twice the velocity, I would guess, and for this one, it's half that velocity.
Yeah, but again, you're guessing. You just said you would guess that it's twice the speed. You haven't measured it. So guessing, it's not a good plan. You have to measure these things. You have to, if you're making claims as to what reality does, then guessing, we could all do that.
Proving momentum is conserved, not kinetic energy. Anyway, so lots of stuff to work on, and I'm of mixed feelings. It's just kind of discouraging, because, like I said, if I don't have a way to detect the velocities, all of this is a lot of, really accurately. It is all kind of for naught.
Yeah, but again, you can. You just have to put the effort in.
You just get a mediocre result. It's not much fun. Let's just put it that way. As much fun. So, the clay thing, I meant to describe that. So the clay experiment, I thought of, just because I happen to have these pendulums and all this stuff, so why not try to use it? And again, it's really, the tricky part is making sure you get the angle, the height right, okay? So the height in gravity has to be, 4 to 1.
Yeah, again, so you're complicating it. You're basically saying you want this height thing in gravity because that's consistent. If you drop something from one displacement and 4 displacements, you get twice the speed. It's very accurate. It's very, you don't need a high-speed camera to measure it. You don't need some sort of, speedometer to measure it or whatever. You just know that they're going to be 2 to 1 ratio in terms of velocity. So then adding that onto a pendulum with an arc and all that, you're making it more difficult for yourself, aren't you?
Okay. And so, preliminarily, okay, so what I did was I have these, the twice mass and the half mass, and I just put a little thin rod on them, and then plowed that into the clay, and just measure how deep the rod goes into the clay.
Right.
And what I'm finding is that
So, in the clay experiments, it's nothing to do with how deep it penetrates. It's to do with how much volume it displaces. So, again, you're trying to work your way around what physics actually does to get the results you want. You're not paying attention.
Be close to the same for the half mass, 4 times the height, is pretty much the same penetration into the clay, the Play-Doh. So far.
But, and
so
again,
it's sort of interesting.
with these heights and the pendulums, you're saying, we're not really sure how to get the 4-to-1 thing. So you're saying it looks like, it seems like, it's pretty similar penetration, which is not the way to measure it anyway, and you don't really know the speeds that you're dropping them at.
I also wanted to redo the Gosling video, but just trying to find ways of doing it better and all that kind of crap, and I haven't really thought of something better. I mean, except for putting a hole in the clay itself and then having the rod through the clay. So at least you're really eliminating any defects that could happen as you drop the weight onto the clay.
I don't even understand what you're on about.
Or any other kind of crap. But who knows? Like I said, I think maybe just poking it might be the better solution. But we'll see. So just more stuff to work on. And,
well, it's not really going to work, is it?
I will say on the lever argument, I mean, I'll replay what physicist Michael's prediction was, but it seems like his prediction is wrong. I mean, I'm clearly getting a lot more than half the velocity on the other side. So when the one mass hits in the, 2 mass to 2 mass or 1 mass to 1 mass.
Again, you're saying, I'm getting a lot more because it looks like, seems like. Have you measured it? Did you measure the distances? Or the lengths of the pendulum the same? Or the weights, equal? Or the distances on the lever equal? Did you force one in more than the other? There's no controls at all. So to say I'm getting more than just on loops alone is going against everything you warn against, isn't it?
I'm clearly getting very close to 80 or 85% of the energy is going into one object, and I would argue that very little energy is left in the other one.
Again, you're making that claim. You're saying I'm getting 80 to 85. So is it 80? Is it 85? Is it 75? Is it 50? Is it 88? You're just making these numbers up.
And there's no subtracting crap. The reflecting energy is the energy missing from the projectile moving. So if I want to know how much I'm losing, I can just look at the other side and say how much is reflecting, and I'll probably find most of it there. Now again, some of it's being lost in the flex of the lever, and that's another problem.
Yeah.
All right, so I try to keep this video short-ish, and I'll take care of other crappy arguments people are making. It's just so bad. I mean, there's no point even. It's just there's a point where there's no point because they're so off the subject. You go to trouble to make these 5-minute videos where you're making the assertion, explaining the situation, one nice little isolated thing, and they just can't stay on that subject, and pretend.
Yeah, but most people can't bloody find him. I mean, your website's a pain in the fucking arse.
And they can. Well, I don't even want to. I won't even go into it, but it's just so. It's as disconnected as when you say, look, show me it taking 4 times the fuel to go twice as fast, and then they start showing you braking distance statistics that don't even match, by the way. Which is like Brozo, who he makes claims that he has debunked something because, well, I found it to be 10% off your prediction. Yeah, it's 150% off mine, but yours is off 10%. I mean, it's that bad. Like he's saying he somehow proved it takes 4 times the fuel, when all he proved is it takes more than 2 times the fuel to go twice as fast. It takes a little more than 2. So because it takes a little more than 2, it means it takes 4. I mean, it's so bad. So illogical. Such absolute nonsense. But anyway, we're going to that in another video.
Yeah, well, we'll leave that to another video.
I can't say I'm losing enthusiasm, but yeah, just like I said, why should these experiments be done this way?
Yeah, I think I'll be losing enthusiasm now if we're just trying to beat nature. I mean, the thing is, like I say, you've argued with all of us, you've called us all frauds and fakes, you've been name calling, just everything you can possibly do to rubbish what we've discovered or what we've seen or what we've observed. Well, not really discovered. I mean, it's 100 years old, but the point being is, like I say, you've argued with all of us and rubbished all our stuff, and now you are losing enthusiasm because it's not working the way you expect it to. Even though you've been shown that it doesn't work that way, you're still determined to prove us all wrong and all of science wrong. And it's, you can't. While you can argue with us, like I say, the only way you're going to get the results you want is to do the very thing that you've claimed we all do, is fake it. It's as simple as that. You're not going to change the laws of physics because you want it to be that way. Your only option is to fake it.
Tying a lever to a sledgehammer, blah, blah. Why? It shouldn't have to be done this way. Fuck. It's just so... It's crazy.
Well,
Stupid.
no, it's not crazy.
It's stupid. It's stupid that you people can't admit that these experiments should be done well and precisely with good equipment.
We have done them well, we have done them precisely, and we have done them with good equipment. And that's the thing you don't seem to understand. That's the thing. Just because we've done it at home and not in a lab, I can put a white coat on when I do my experiments, but it won't make it come out any better.
Where you can verify things by different methods and be sure that the result is what it looks.
People have done experiments different ways between us, between Stephen Brough, Despard, Miles Marbles, myself, Ian Gosson. We have done experiments in all different ways, and they all verify the same thing.
Anyway, till the next time and such.